I've decided that however far we get today, whether we get to the entire section 4.7, or if we don't get to it at all, we're just going to move on. Okay, so next time we'll be starting on chapter 5, right? So it did say in the schedule, I need to update the schedule because I'm pretty sure it's pretty far off at this point, but it did say in the schedule we would cover the application sections 4.8 and 4.9, but we don't have time to because I'd really like to get to chapter 6 and we're running out of days, as you might have noticed. So yeah, so we will be moving on and skipping those. But let's see. Yeah, I know it happened so quickly. Okay, so today we have one more thing to talk about from the previous section. So that was section 4.5, and that's just the basis theorem, which is something we've talked about before. So we're just sort of restating it for abstract vector spaces, but it's going to be exactly the same. So this is the basis theorem, right? And it says that if you have a vector space V, we'll say is k-dimensional, or is a k-dimensional vector space, right? Then any set of k linearly independent vectors forms a basis.
What section is this?
This is from 4.6, no, 4.5.
Okay, it's still 4.5.
Yeah. I'll put that there. So this is from 4.5. Okay, so that's just saying that if we already know the dimension of this space, then we can just check a set for linear independence and then it has the proper number of vectors and we don't have to check we don't have to check that it spans the space, right? That was the other condition in the definition of basis. So this is just a little bit different, right? Than checking just from the definition. Also, any set of exactly k elements that spans V will form a basis. Okay, and so that is saying that if we know that it has the right number of vectors and it spans V, that we don't need to check for linear independence, right? So it's sort of saying that we only need to check for one or the other so long as we know the dimension of the space and we know that what we're checking, the set that we're checking, whether or not it is a basis, we know that number of vectors matches the dimension of the space, right? Okay, so we're not going to prove this one. I think we did go over this earlier in an earlier section, but yeah, this was all we needed to cover from 4.5. And so now we're going to move on to 4.6. And we're going to be talking about rank. So remember, the rank of a matrix is the dimension of the column space, right? So we talked about this before. So if A is an n by m by n matrix, we said the rank of A is the dimension of the column space. And also we talked about the nullity of A, which is the dimension of the null space. Right? And we also have the rank nullity theorem, right? So the rank nullity theorem says that the rank of A plus the nullity of A is equal to n, where here n is the number of columns of A, right? Because A was an m by n matrix. Columns. Okay, so we've seen this before. Now we did talk about the range and kernel of a linear transformation. So we can restate this same theorem, but just in terms of the linear transformation that corresponds to A, right? So that has the matrix A. So this is the rank nullity theorem for linear transformations. And so if we have a linear transformation, we'll say from a vector space V to a vector space W. So if this is a linear transformation, and the dimension of V is equal to n, and the dimension of W is equal to m. That one isn't as important really, but that's fine. Then what this says is that the dimension of the range of T plus the dimension of the kernel of T is equal to n. And here n is the dimension of V, the domain, right? Okay, so this is actually just saying the same thing, right? So this corresponds to the rank, and this corresponds to the nullity of the matrix A that describes your linear transformation, right? Okay. One thing to note that I'm not sure we mentioned before, so let's just say it now. So the rank of A, of a matrix A, if it is m by n, is less than or equal to the minimum of m in n, right? And this is because the rank of A is the number of pivot columns of A. And you can't have more pivot columns than you have rows, and you can't have more pivot columns than obviously you have columns, right? So this is the reason why, right? Okay. So there is another space that we can talk about that corresponds to a matrix, right? And this is called the row space. Of a matrix. And just like, so this is very similar to the column space, but now this is going to be the span of the rows. Okay, and we're just going to denote this row of A. right? Okay, so if A, again, is an M by N matrix, then we know that, first of all, the column space is a subset of Rm, right? And then the row space will be a subset of Rn, right? Okay, so these do live in two different spaces, right? So this is, if you're thinking about this as a linear transformation, the row space is on the domain side, the column space is on the codomain side. Okay.
Wait, can you go back to the rank nullity theorem in terms of
Yeah.
the linear transformation? How's the dimension of range T just the rank?
So if you think about the range of T is the image, right? And you can also think of the rank is the span of the columns.
Right.
Right? So if you're looking at T of X equals A times X, everything that comes out of here is equal to some linear combination of the columns, right? Because this you can rewrite as X1, A1,
Right.
A2. Right, yeah. So the range, so anything that you can get as an output of that function is a linear combination of the columns.
Right. Oh, okay. And what about the kernel? Is that
Right, so the kernel of T, so the nullity is the dimension of the, okay, so it's the dimension
null
of the null
space?
space, it's the,
Oh, which is the same thing as the kernel of T. Yeah, makes sense.
right, yeah, yeah. So that's, yeah, the kernel, they're very similar, right, in definition, so. Okay, that makes sense to everybody? Okay. Let's see, so, okay, so we have this notion of row space, right? And it's not too hard to show that if you have two matrices that are row equivalent, right? So if we get B by performing some row operations on A, then that doesn't change the row space. So the row space of A is equal to the row space of B. Moreover, if B is in row echelon form, then the non-zero rows of B, non-zero rows of B form a basis for the row space.
Is this?
Okay.
Oh, okay. I wasn't sure if you get to say it's a basis for the row space row A.
Yeah, for the row.
That's nice.
Yeah, exactly. Yeah, so this tells us how to find a basis for the row space, right? We just row reduce. We can stop at once B or once our matrix is in row echelon form, and then we just pick off the non-zero rows, right? So let's do an example of this. So say we start with a matrix A. Let's see, 1, 3, 2, 1. Right? And then we can notice that the bottom row is a constant multiple of the second row. So when we row reduce, that will actually just go away. So we get a row of zeros, right? And then to get this in row echelon form, we just need to take row 2 minus row 1. And that will give us 0, 1, minus 1, minus 3. Okay. And we have 2 non-zero rows, right? It's the first 2. So our basis for our row space, we'll just write it this way. So our row space is equal to the span of, and since we are using these, I'm going to write them as row vectors. Usually we write things, or up to this point, we've been writing everything as a column vector, but it's more natural to write it this way. So, but if you really want to, you can just take the transpose, write it as a column vector. This is 0, 0, 1, minus 1, minus 3. Great.
Oh, so we have to write the vector like that, as in horizontally?
Yeah, well, you can. And we often do, because when we're talking about the row space, we kind of
Okay.
use row vectors. So this is a row vector, but you don't have to if you really hate it. It's not that big a deal. Okay. So a basis, I'll write it this way. So the basis for the row space of A is these 2 vectors. And I believe in the textbook, when they write something as a row vector, they use, so I'm making a note. In the text, they'll write it like this, like as a n tuple, right, with the commas in there. So just so you know, that's what it looks like in the text.
I like it in the textbook
Mhm.
because it makes me think it's like a coordinate point.
You prefer that? I think you're muted.
Oh, sorry.
You're fine. Okay, so this is the basis for the row space, right? So it's not too much work to find, right? Since we already have it in row echelon form, we can write down the basis for the column space as well. So let's go ahead and do that. The column space corresponds to the pivot columns. So we have pivots here and here. And so those correspond to the columns in the original matrix right here and there, right? So the column space is equal to the span of 1, 1, 3 and 2, 3, 6, right? And so if we want to write this as a basis for the column space is just the collection of these 2 vectors, right? Okay.
I think it's 1, 1, 2. It's not that important though.
Oh, it is 1, 1, 2. Thanks. Yep. Okay. So one thing, so a couple things to note. First of all, that the row space of A is equal to the column space of A transpose, right? So if you think about what happens when we take the transpose of a matrix, the rows and columns switch, right? So all of the columns of A become the rows of A transpose, right? So you can see, or maybe let's say it this way, all of the rows of A become the columns of A transpose. So the row space of A is the column space of A transpose, right? Okay. Another thing to notice. So consider an n by m matrix. Oh. Maybe this is so an m by n matrix A, and suppose the rank of A is some number R, right? Then the number of columns, the number of pivot columns of A is equal to R, right? That's just by definition of rank. And we know that the number of non-zero rows is also R, right? Because if you think about, okay, so if you have a pivot, that must correspond to a non-zero row, right? And if you're, so it is important. Number of non-zero rows in the row echelon form of A, so it, of A is R. Okay, so when it is in row echelon form, all of the non-zero rows correspond to rows that have pivots in them. And for every one of those, you get a pivot column, right? So in fact, what this is saying is that the dimension of the row space is always equal to the dimension of the column space, which is the rank, right? Okay. So the row space and column space will always have the same dimension. Okay. Also, if you look at, okay, I'm going to draw this down here. Okay. So there's a way to sort of visualize how these spaces fit together. So I'm going to try and draw this nicely. Okay. So this is sort of like an abstract picture of what's going on. And these squares are meant to, or rectangles, are meant to represent subspaces, right? Okay, and it looks something like this, right? So every subspace contains zero, so we can just imagine that this is the zero vector right here, right? And then they're sort of like branching off from here. Okay, so on the left-hand side, we have Rn. On the right-hand side, we have Rm, and we're considering an m by n matrix. So its column space lives in Rm, right? And we know the null space lives in Rn over here, right? The dimension of the column space will still assume that the dimension is this number R, right? So this dimension is R. The dimension of the null space by the rank nullity theorem is n minus R, right? And then we have in Rn is the row space of A, and its dimension is also R, just like the column space, right? And then we have this one last subspace over here, it's in Rm, and this will be the null space of A transpose. And remember that this is the null, or sorry, this is the column space of A transpose. So we sort of have these like corresponding subspaces, right? Okay. Oh, and
Go
then
back to the note.
Oh,
Scroll up a little
yeah.
bit. Yeah, that one. Copy that.
And then the dimension of the null space of A transpose is M minus R, right? And we can just use the rank nullity theorem for A transpose to figure that out. Okay. So this sort of decomposes these two spaces into 4 subspaces, right? And they're all related. We haven't yet learned this term, but we will eventually. So I'll just say this now. These spaces are orthogonal. These two subspaces are orthogonal, and that essentially means that they're at right angles to each other. There's a, an actual definition that is proper and is more general, but that's how you can think of it for now. And so these are also orthogonal.
That makes sense because you could say it's the call A and null AT, but you could also say it's row AT null AT.
Right. Yeah.
So it's the same pattern of relationships as the previous one.
Right. Yeah. Yeah, it is. Okay. So, yeah, this is the row space and column space. There's also a nice picture in the textbook that's a little less abstract than this one, but it's harder to draw, so I won't. But in the text on page 236, there's a nice picture of this in R3, right? So that you can actually picture it. Okay. All right. How we do? Okay. Let's see. Let's do an example. So we're going to find a basis for each of these spaces. Well, really the important ones are the row space, column space, and null space. So we'll focus on those. If we have a matrix A, let's see, it's 1, 2, 3, 1, 0, 1, 2, 0, 1, 2, 3, 1. Okay, so if we're looking at this matrix, we want to find a basis for those 3 spaces. So the row space of A, column space of A, and null space of A. Okay. So for both the row space and column space, we're going to want to row reduce this matrix. So let's go ahead and do that. So first of all, the third the third row, okay. The third row is exactly the same as the first row, right? So we can get rid of it. It will become all zeros. Oh, this is a 1, 2, 1, 0, and all zeros in the last row. And then we can take row 2 minus row 1. And that will give us 0, minus 1, minus 1, 0, 0. And just to make this nicer, we can multiplied by -1.
Could you also like reduce this even further to like
Yeah, we could. Let's go ahead and do that. Why not? Okay, so for the row echelon or reduced row echelon form, we would get 0, 0, 0, and that would be 1, 1, 0. You guys agree?
did you replace the first row with the first row minus 2 times the second row?
Mm-hmm.
Okay, yeah, I see it. Yeah, I see.
Okay. Sorry. I didn't- Okay. Let's see. So, okay, we have this.
I think this is reduced.
Yeah, it is reduced.
Yeah, it's reduced.
So we can stop. And we know that the row space of A is equal to the span of these two non-zero rows, right? So 1, 0, 1, 1, 0, and 0, 1, 1, 0, 0. And that this is a basis. So basis for the row space is just these two vectors. And 0, 1, 1. Great. Okay, so that's row space, and the column space is going to be the columns from A that correspond to our two pivot columns, right? So two pivots. So here and here. And so I'll just skip to writing this so as a basis. So the basis for the column space is 1, 1, 0 and 2, 1, 0. Oh, wait, no, I took those from the first step. Sorry. This is A. So it should be these two right here. Okay. Right. So those are 1, 1, 1, 2, 1, 2. Okay. And it's good to check. So we do have two vectors in the basis for the row space and two vectors in the basis for the column space. So those should be the same, right? And the rank of A is 2. Okay. And then we also want to find the null space. So we need to solve the homogeneous equation, and we already have this in row echelon form, so it's not too bad. We get x1 plus x3 plus x4 is equal to 0, and also x2 plus x3 is equal to 0. And then the other x3, x4, and x5, well, actually we have x3, x4, and x5 are free. Okay, so our general solution will look like x1, x2, x3, x4, x5. So this is a vector in R5. And then let me just write this out. So this is x1 is equal to minus x3 minus x4, and x2 is equal to minus x3. So if we plug those in, we get x3, x4, and x5. And so we can split this into three different vectors. we get minus 1, 1, 0, 0. And then we get minus 1, 0, 0, 1, 0. And x5, which is 0, 0, 0, 0, 1. Okay, and so this is going to be the span. So the null space is going to be the span of these. Right. And the actual basis is just those three, right? So the basis for the null space of A is just this set containing the three vectors. Okay, so that is the basis for each of those spaces, right? Yep. And then we can double check, okay, there are three vectors in the basis of the null space. And so the nullity of A is equal to 3, and the rank plus nullity is 2 plus 3, which is 5, and 5 is the number of columns of our original matrix, right? Okay. So we have some things that we can add to the invertible matrix theorem. So we're going to go ahead and do that now. And these are just going to be statements involving the rank and nullity, right? So so remember, the invertible matrix theorem is all about these different equivalent conditions to having an invertible matrix. So we assume that A is a square matrix. So A is n by n. Then the following are equivalent to A being invertible. Okay, so this is true if the columns of A form a basis of Rn. So if they form a basis, that's the same thing as saying that they're linearly independent, right? Well, it's not exactly the same thing, but it means that they are linearly independent. This is also equivalent to the column space of A being equal to all of Rn. And that is the same as saying that the column of A is, or the dimension of the column space of A, which is the rank of the matrix A, is equal to n. And then that's equivalent to saying the null space of A is trivial. So it's the subspace that just contains the zero vector. And lastly, we have that that's equivalent to the dimension of the null space being 0, which is just the nullity of A. Right? So these two things are equal, and they will be 0 if A is invertible. Okay. So that concludes section 4.6. That's everything we're going to talk about from that section. And then we are going to talk a little bit about 4.7, and then we'll take the quiz. So 4.7 is about change of basis. Okay, so we have, so we've talked about bases and about representing a given vector in terms of a basis, right? So we're going to talk about how to go between different representations of that vector in terms of different bases, right? So say you have two bases, B1 up to Bn, and we use A1 up to An of a vector space V. Okay, so assume you have two different bases. Then you can or then there exists a unique matrix so this will actually be n by n, unique n by n matrix. The notation for this is P, and then you have A, a backwards arrow, and B. And so this is going to be the matrix that changes your coordinates from B to A, right? This is such that your representation of your vector x in terms of A, right? So the A coordinate vector is equal to this matrix P times the coordinate vector in B, right? Okay. And furthermore, we can actually write down what this matrix would be. It is just the matrix of each of the basis elements from B written in terms of coordinates of A, right? So that's what this is right here. This is the first vector in the basis B written in terms of A. And then we have the second column of this matrix is the second basis vector from B written in terms of A, and so on. And when we put these all together, these form our change of coordinates matrix. Okay, so why might this be the case? Why does this P matrix have this form? Well, we can see this by looking at our vector. Say in B coordinates, it has the coordinates C1, C2, up to Cn, right? So this means that this coordinate vector is just this vector like this, C1 up to Cn. Okay. And then we want to end up with the coordinate vector in terms of A, right? So we can express that by writing this as, we know what its coordinates are in terms of B, so let's write that out. Right, this is equal to this linear combination of B's, or BI's. So we want this in terms of A, right? But we can split this because it's a linear combination. We can just rewrite this as C1 times B1 in terms of A plus all the way up to Cn times Bn in terms of A, right? And then we can interpret this as a matrix multiplication, right? So this is the columns of a matrix. So we can write it like this. Oops, not plus. Right, so we get this matrix times the vector C1 up to Cn. Okay, and this is exactly what we claimed was that matrix P, right? So this will give us P from B to A, and this is just our coordinate vector that we started with in terms of B. Right? So we see that we get that X written in terms of A is equal to this matrix times X written in terms of B. Okay, so a couple of things to note. First of all, we saw something somewhat like this before, which we called a change of coordinate matrix. So this generalizes the change of coordinate matrix that we saw before, this P sub B, which was just where we took all of the basis vectors and put them into a matrix, right? And we call this a change of coordinate matrix. This is the change of coordinates in Rn from the standard basis. That's the one where we have these standard coordinate vectors, E1 up to En. So from this basis to the basis B, which would be your B1 up to Bn. Okay, so you can see that this does agree, right? The B coordinates are already written in terms, or so the B vectors are already written in terms of the standard basis, right? So when we do this, when we try to write it this way, or rather, I guess, this way, our work's already done. They're already written in terms of the standard coordinates. Okay. All right, so there's that. And also, to actually find P, what we can do, so practically, when you want to find P, you can row reduce the matrix A1 up to AN. So you take A1 up to AN, so all of the columns from the basis A, and you augment with all of the columns from the basis B. And when you row reduce this to get the identity on the left-hand side, you get your change of coordinate vector or matrix on the right-hand side. Okay, so this is,
Pardon me.
yeah, go ahead.
Maybe my brain broke, but I can't figure out what's going on in the line where it says to curve VP, and then there's a line, and then V1 through Vn. Is that just an equals sign? Did my brain break?
Oh, This right here,
Yeah.
yeah, that's an equal sign.
Okay, sorry.
You're fine. Okay. Right, so to find this, we row reduce like this, and this is very similar to finding finding A inverse by row reducing A augmented with the identity matrix, right? Okay. We're doing on time. Okay, so we're gonna do a very quick example of this. So you can take, so say you have two bases. B will be 1 minus 3 and minus 2, 4. And A will be minus 7, 9, and minus 5, 7. Okay, and then so we want to find matrix from, let's see, from A to B, right? So we're looking for P that changes A to B, or let's go from B to A, since that's okay. I don't know why the textbook writes it backwards, but I'm just going to be consistent with that. So, okay, so we're looking for this, right? And we can set up an augmented matrix, right? Where, so if we're going from B to A, we want to put the vectors from A on the left-hand side, right, of our augmented matrix, and solve, and then augment with the vectors from the basis B, and then want to row reduce this, right? Okay, so yeah, this might get messy. Okay, we'll see. What do I want to do? Okay, let's see what happens if we do. Just get this 2, 2, minus 2, 2. Right? 2, 2, minus 2, 2. Yeah, okay, so if I just add row 1 and row 2 and replace row 2 with that, I get this, and then I can, yeah, I'll just divide by 1 or 2 and switch these. And then, yeah, switch rows. So 1, 1, minus 1, 1, 1, minus 2. And we'll do row 2 plus 7 times row 1. So that's 0. 2 6, negative 6, yeah, 5. Okay, and then yeah, we're almost there. So divide by 2, 0, 1, minus 3, minus 5 halves, and then we take row 1 minus row 2. Then we have our identity on the left-hand side, and then we just have to figure out what the right-hand side is going to be. And that is going to be, so it's minus 1 minus 3, so plus 2. And then it's 1 minus negative 5 halves, which is 1 plus 5 halves, 7 halves. Do you guys agree? Okay, cool. So that is our answer. Mhm. Oh,
I think
there's a mistake.
there's a negative sign that appeared on the 5 when it got divided by 2. It became negative 5 halves.
Oh yeah, it shouldn't have been negative.
Not that I haven't done the same thing a million times.
Yeah, that's fine. Okay, so this does. Oh geez. Okay, so it's 1 minus 5 halves, which is 2 minus 5 over 2, which is minus 3 halves. Okay. There we go. So that means that this is our matrix. 2 minus 3 halves, and 5 halves. And that's all we were looking for. We weren't looking for the change of coordinates for a particular x. But if we wanted to do that, all we do is multiply by this matrix, right? Okay, so that is all I'm going to say about section 4.7. Yeah, that's it. And then we have the quiz, which I need to post.